So there are certain like famous experiments that you need to know just because they played such an important role in how we got to where we're at. So, for example, you had Galileo and dropping the two different sized cannonballs off the Millikan Tower of Pisa. Disproved Aristotle, introduced that shifted the whole paradigm of how science was done. You could no longer just say, well, why do you think that? Well, it makes sense. It seems logical. No, you had to have empirical proof for that. You had Dalton, who proposed the atomic theory. Okay? He was the first one that came up with a working idea. You had J.J. Thomson, discovered the electron. You had Ernest Rutherford, who came up with the structure of the nucleus. Along those same lines is what's known as the Millikan oil drop experiment. So what came out of this, and this video is also cool because it shows you the technique on how they actually came up with these values of charge. Because it's incredibly difficult. I mean, you look and say, okay, hey, here's an electron. Great. We've talked about it probably since elementary school. You all have been taught, oh, there's electrons, protons, and neutrons. Okay? And there are, we think. Best we can tell. But in terms of actual proof, and I can't show you an electron, okay, I can't even show you an individual atom. Maybe it's big enough, but you can see like in a lattice. But certainly not a single electron. And so to try to isolate that electron and find its mass, because it isn't like we can take an electronic scale and go, oh, I'll grab an electron and I'll put it on the scale. There we go. There it is. We got it. Okay? So the mass was difficult to find. And the value, the charge, was also difficult. Because it isn't like, oh, we can put it on a charge scale and we go, oh, here's the charge. 1.60 times 10 to the negative 19. And it was harder on the electron because it was so small. But then, the weird thing was, then we figured out the proton, which is much more massive. It also has the exact same quantity of charge. But, so obviously the charge isn't proportional to mass. Right. And then you have neutrons, which are basically the same mass as a proton, but they don't have any charge. So it's just like this. So this is why once you really get into studying quantum mechanics, it gets weird. Okay? So how can an electron, which is such a small fundamental particle of nature, have the exact same charge as a proton, which is 1,800 times greater? And then how do you calculate the value of that charge? So this is what comes out of this experiment. So it's a good news, bad news day. Okay? Yes. Actually, it's kind of a good news. You're not going to have any homework tonight, and you're going to watch the video. So, yes. Kind of
guys, hear me out. Just call him Stanley. What did you get? We all call him Stanley.
I gotta be
the music is a little suspect. Just show my idea when I
can't take this seriously. What is that? What am I watching?
Are we back in the dark and Yo, I can't.
These graphics are crazy.
Oh, it's just space. I don't know what he's doing. I can see what he's doing.
What are they doing? This has nothing to do with what we're
How
talking
did the
about.
cameraman get out there? How did the cameraman get out there?
Dude, the cameraman's like, oh god.
Yeah.
Cameraman never dies.
It's pretty crazy.
I can almost remember.
The cathode ray tube was invented in the middle of the 19th century. Of course, course, it eventually became the modern television tube. But before that misfortune, it actually served a useful purpose that I'd like to tell you about. Here is a particularly simple cathode ray tube. It consists of an evacuated glass tube with 2 electrodes inside. I'm going to apply 20,000 volts across those 2 electrodes, but first I have to turn out the lights so you can see what happens. Okay. Now you see what happens is that it glows inside, and also this Maltese cross casts a shadow on the end. The Maltese cross is the positive electrode. I'd like you to notice something else about it too. I can easily move around the shadow just by bringing up a simple bar magnet like that.
What are we supposed to do?
Okay?
For the shadow, bud.
Right from the beginning, people suspected that that glow was actually a beam of charged particles because it was so easily deflected with an ordinary magnet. But to prove that that was true, you would have to deflect it also with an electric field. And for some strange reason, that didn't work. Then along came a British physicist named J.J. Thomson. Thomson was a brilliant experimental physicist, but strangely enough, he was very clumsy. In fact, the legend is he broke every cathode ray tube he ever touched. This is a replica of Thomson's tubes, and like one of his own, it's also broken. Thomson realized that the reason the electric field didn't work was because the vacuum in the tube wasn't good enough. And he also figured out that the reason the vacuum wasn't good was because of gas that was stuck on the walls of the tube when the glass blower sealed it off. And he figured he could solve that problem by heating the tube as it was being sealed off. And so he had the tubes placed in an oven to be heated while the glass blower was sealing it. And that trick worked. After he did that, the electric field deflected the beam. And so Thomson was able to show that the beam was made of electrically charged particles. And he quickly showed that the same charged particles came from every kind of matter. What Thomson had done was the first splitting of the atom. He had shown that the ultimate indivisible particle of matter really had internal parts after all. The honor of naming the new particle should have gone to its discoverer, J.J. Thomson. And he wanted to call it the corpuscle. But that name didn't stick because it really had already been named. It was called the electron. And so, J.J. Thomson split the atom and discovered the electron by baking his tubes. This name, the electron, started a tradition in physics of naming things with individual units with names that end in ONS. So that, for example, the individual unit of light is called a photon, the unit of sound is called a phonon, the unit of matter is a proton, and we have neutrons, and so on. In fact, recently sociologists have discovered that even human populations have individual units called persons.
And then if it's a solid, you have protons.
Once the crucial job that we made was to measure the electric charge of the electron. And that job was done in one of the classic experiments in all of physics by the great American experimentalist, Robert Andrews Millikan.
Never heard of him.
This is why you're
A small
watching.
beaker of oil. A sturdy iron pot. Just enough power. A dash of discipline. A measure of creativity. And perhaps a touch of genius. These were the essential ingredients in the physicist's very experimental recipe.
So it's just like an alternate.
The scientist, Robert A. Millikan. The achievement, measuring the value of the charge of the electron. The Preparation time, almost half a century. 1868. The year a young nation still shaky from the Civil War was linked together by the Transcontinental Railroad. That same year, Robert A. Millikan was born, the son of an Iowa preacher. He set out across the plains for Ohio to study the classics at Oberlin College. Later, because there wasn't an opening to teach Latin or the history of ancient Greece, he became an instructor of elementary physics there. He showed promise. Columbia University awarded him a fellowship in physics, which he lost after
Nice
the first year.
mustache.
The loss of support made him doubt, but not give up on his ability as a scientist. He went back to the Midwest, where he studied under Albert A. Michelson at the University of Chicago. Michelson had been awarded the Nobel Prize for developing an extraordinary instrument to measure distances by the interference of light waves. Millikan wanted more than a summer session in Chicago. He wanted to launch his career in physics there. To prepare himself further, he visited a number of legendary universities and laboratories of the Old World. Before North America achieved prominence, Europe was the continent that most inspired scientific discoveries. Before the First World War, Millikan's inspiration was molded not only by the long shadows of Newton and Galileo, Kepler and Copernicus, but by the fact that he himself could walk among the living giants of his own day.
So,
The Englishman William Ramsay, who discovered helium, neon, xenon, and krypton. Wilhelm Röntgen, German discoverer of the X-ray. Guglielmo Marconi and Karl Braun, who developed the wireless telegraph. Like Leibniz and Newton in calculus, they made their discovery at the same time, certainly not together.
so
Albert Einstein, Max Planck, and Johannes Stark were hard at work in Germany. But the greatest direct influences on Millikan seem to have been British. J.J. Thomson and his student H.A. Wilson at the Cavendish Laboratory. The electron, X-rays, and radiation. Such discoveries made physics an exciting frontier, and he was eager to cross its threshold. Yet Millikan was nothing if not careful in his work, and it would take a decade before he began to make his mark in the world of science. He was already in his 40s and had only just become an associate professor at the University of Chicago. But about the same time, Marie Curie was awarded the Nobel Prize in Chemistry. She'd already received one in physics. He began to measure the charge of an electron. His groundwork had been laid by Thomson, a Nobel laureate in 1906 for his investigations on how gases conduct electricity. This brilliant Englishman had discovered the electron and developed the cloud method to measure its charge. This chamber was invented to study atmospheric clouds, but in the hands of Thomson and his colleague, H.A. Wilson, it had gone above and beyond its original purpose. A sudden expansion of air, saturated with water vapor, forms clouds. If there are dust particles on which to condense, that supersaturated vapor would also condense on ions. Electrically charged particles created by an X-ray tube. Each drop of water would have the electric charge of a single electron. With this insight, Thomson and Wilson set out to determine the average charge on an average droplet. The cloud chamber method was difficult. The experiments, which involved measuring the rate of fall of the cloud in an electric field, were subject to countless uncertainties. Nonetheless, they finally obtained an estimate of the electron charge. Only an estimate. But it was correct in its order of magnitude. To a man like Robert A. Millikan, it was an open door to his particular talent. precise measurements of the most fundamental physical quantities. Millikan repeated Wilson's experiments at the University of Chicago. To ionize the gaseous cloud in the chamber, he used X-rays at first and then small amounts of radium. He tried a more powerful electric field in the chamber. If this worked, it would be powerful enough to balance the force of gravity and to keep the cloud suspended without motion. Now, all this looked pretty good on paper, but when things got moving, there was a little problem. With such powerful electric forces in the chamber, the water vapor cloud quickly disappeared. But Millikan turned this problem into an advantage. When the electrical field was turned on, individual droplets stayed in view. Millikan imagined measuring single water droplets rather than an entire cloud. If it were possible to make measurements on the droplets, the effects of individual electrons could be detected. A brilliant insight, but not without a problem. Water evaporates. Instead of water, Millikan wondered, why not use droplets of oil? Oil, unlike water, doesn't evaporate. In 1907, at the University of Chicago, it began to fall into place. Given the apparatus to produce a mist of oil, Millikan was increasingly confident that the electrical charge of an electron could be accurately measured. Under his guidance, Harvey Fletcher, a graduate student from Brigham Young University, suggested an atomizer. Fletcher's first apparatus for the oil drop experiment, like Millikan's original idea, was simple, powerful, and altogether brilliant. It was a combination that began to work. The essence of the experiment is to apply an electric field to an electrically charged drop of oil falling through the air, and then to analyze the result using Newton's powerful equation, F equals ma. The mass of the drop times the acceleration is equal to the sum of all the forces acting on it. What forces act on a falling drop of oil? There's the force of gravity, of course. And then there's the effect of viscosity. An oil drop, if only for a millionth of a second, has the acceleration of a free falling body. But after that first millionth of a second, the oil drop reaches terminal velocity. Like any sphere falling through a viscous fluid, it falls at constant speed. The viscous force on a moving sphere, worked out by the English physicist George Stokes in the 19th century, is equal to 6 pi times the radius of the sphere,
This is why we
times the
don't do it with
viscosity
drag
of the air,
coefficients and normal
times the
physics,
speed of the
because
sphere.
it just gets real ugly real
Very
fast.
quickly, the speed grows until the viscous force is big enough to balance gravity.
That's a lot of letters.
In
Why do
simple
I tell them
terms,
it's terminal
the sphere
velocity?
falls at constant speed.
Ooh-wee.
Millikan had to measure
This is
the
why
speed
we don't deal
in
with
order
that.
to find out how
Are we
big
going
the
to?
drop was.
Huh?
Are we going to?
Even with a powerful telescope,
We're not
an
again. That's
individual
the
drop was too small to
That's
see.
a top level color.
What Millikan saw was like a star in the night sky, a pinpoint of light that couldn't be resolved into its spherical shape. But by watching his star drift slowly from one scratch mark to another on his telescope,
What's so funny over there?
and using the known density of the oil, he could measure its precise size.
Yo.
Yo.
That actually checks out.
No, I don't think it does.
Oh. Okay.
I don't think
Yo.
it's working.
No.
Yeah, I wish I could do that on my board.
Now he would turn on the electric field and create an electric force equal to the electric field strength times the charge on the drop. That's the charge Millikan was really after. Due to one electron, or at most a small number of them, It would be an integral
That's what we
motor
talked about,
of the
that's the
fundamental
value
unit of
before
electric
force
charge.
effect. They have a
With the
key
electric force,
You only
it could
reduce
drive the
effect.
drop upward until, once again, it reached a constant speed. Together with the speed he'd measured with the field off, the new speed gave him everything he needed to find the charge.
On and off.
Yo,
What the heck?
I don't like this manipulation, Mr. Millikan.
I know.
love the ragtime.
I wish I had like my own band,
The
like a
experiment
band would play
designed
when
with
I
the
was
most
solving
exquisite care.
Oh, we can do that. Let me say it.
Who's we, bro?
Minimize
Me and Ken,
turbulence
we got
drops as they could.
Me too.
Like a target.
Wait, what? What can
A heavy iron pot was designed to house and protect. Air would be filtered through glass wool before entering an atomizer designed to spray the finest mist of oil droplets into the chamber. Even the light to illuminate the droplets was filtered. A solution of copper sulfate and a meter-long tube of water would remove the light's excess heat. As the time came, Millikan saw to it that nothing would disturb his experiment. Stopwatch in hand, hour after hour he would peer through his telescope, through the
No, he should
portal,
do it.
and into the chamber.
Why is he not doing it?
Deep within the heart of the chamber, you would see a single charged droplet of oil, glowing like a star. Under the influences of gravity and viscosity, the droplet would fall. Down through inner space, the star would fall until it would reach the top scratch mark, and Millikan would start his stopwatch. It would keep falling until it would reach the bottom mark.
but effective. Right?
Millikan would enter the time it took each drop to fall.
An average of
And he
I
turned
don't
on
think
the
it's two
electric
decimal
field,
places.
turning the oil droplet into a rising star. At the bottom mark, he'd start the watch, letting it run until the rising drop would cross the finish line on top. Again and again, he'd record how long it took to rise and fall, often observing a single droplet hours on end. Hundreds of measurements were taken, recorded, mused over, and eventually analyzed to give the most accurate measurement ever made of the fundamental unit of electric charge.
And
Millikan's
this
final
was
published
without
measurement,
spreadsheets.
4.77 times 10 to the minus 10 electrostatic units, was only 2% different from his result prior to using oil in the experiment.
Am I right?
Robert A. Millikan's forte
Well, why didn't you say obvious?
ability to detect and eliminate error, and with extraordinary diligence and creativity to improve on existing tools. In public statements, and there were many as he became an elder statesman of the academic community, he used every opportunity to extol the scientific method. The scientist's responsibility was to make measurements without bias, and to let nature dictate the answers. The scientist's job was to make each measurement, no matter how painstakingly, and to publish everything, determining the significance of the data. That was the job of the scientist's peers. Millikan's peers understood the significance of this work. In 1923, he became the first native-born American to be awarded the Nobel Prize in Physics.
no way.
Millikan went on to head the California Institute of Technology, an American institution, and to become one himself. His name became and remains synonymous with scientific progress.
Being Gavin.
In the first half of the 20th century, his image, next to Albert Einstein, was that of the most famous physicist
Einstein.
in North
Yeah, big
America.
time.
That's a sign.
I'd also like to show you what the experiment itself looked like. There's one thing I particularly want you to notice. This canister right over here. If it looks familiar to you, it's because the same one is right there at the end of the bench. That's Millikan's own oil drop experiment, still functioning after all these years.
Ah,
Does he have that?
Now I have something truly extraordinary I would like to show you. When Millikan did his experiment, he gathered together his results and he wrote them up to be published in a scientific journal for all the world to see. But before that, while he was all alone in his laboratory, he had to have a place to write down the results of his experiment as he was doing it. That place was his laboratory notebook.
It was never intended for anyone else to see. It was for Millikan's eyes only. This page is dated Wednesday, December 20th, 1911. Here, Millikan writes down the temperature and the pressure. And here, under the letter G for gravity, a series of figures, each one of which is the time it took his oil drop to fall between the two scratch marks on his telescopes. Then, a similar column under F for field, the electric field. And again, the times it takes his oil drop to fall.
yeah, no spreadsheets, all written out by hand.
He calculates velocity,
Yeah, I could do that.
V1, V2,
That's
and
no
so
different,
on.
bro.
Using those
Yeah, I
velocities,
think you are, Dick.
he finds the logarithm of V1 plus V2, so he can add it to 1/2 the logarithm of V1. And finally, here,
Log out.
Millikan reaches his result.
Bro forgot to add.
And then he writes, "This is almost exactly right." But how can he say that? He's supposed to be measuring a fundamental constant of nature, whose value he doesn't know in advance. Why does he say, "This is right"? On another page, he writes, "Beauty." On this page, "Beauty, publish." And another, "Very low, something wrong." And then he makes a very revealing note. "Not sure of distance, 1.273. There it is. When he gets a result he doesn't like, he doesn't throw it away because that would be cheating. What he does instead is to examine the apparatus to find something wrong. So he has a reason for throwing it away. Of course, when he gets a result that he does like, he doesn't examine the apparatus nearly as carefully to find out what went right. Obviously, that creates a powerful bias in his method to get the result he wants. Another page. Here. Best yet. Beauty. Publish. And so on. For pages and pages
Did he have a
and pages.
calculator?
Huh?
Did he have a calc?
The point is not
Not
at all
1911.
that Robert Millikan was a bad scientist.
You would have had a
He
slide
wasn't.
rule.
He was a great
Did he
scientist.
use an abacus?
Probably more of a slide
But
rule.
by examining these notes, we can get a brief insight into how science is really done. What Millikan was doing wasn't cheating. He was using his scientific judgment. And in fact, it must be that way. Because no one ever stumbles onto a scientific discovery. Every discovery is made in the course of an experiment that was exquisitely designed to give the results that the scientist expects to find. And the scientist knows that quite possibly fame and other rewards will be waiting if a great discovery is made. But then, what prevents someone from making a discovery that isn't real? The answer is, the experiment can be repeated somewhere else, by someone else. to see
That's
the
the
truth.
whole key to a good science.
It's often said that the immense success of some scientific enterprise was due to something called the scientific method. And that a key part of that method is the unprejudiced, dispassionate collection of scientific data. And that if other fields were able to imitate that magic scientific method, they could be just as successful. Well, in fact, that just isn't the case. Passion and prejudice are never very far from the scientific process. The safeguard is not disinterested science, but rather the fact that all scientists believe at the very core of their beings that experiments can be repeated.
And if they can't, it's not good
That
science.
belief is the central tenet in every scientist's faith.
And I have faith that you'll be back here next time.
Okay. You have no homework.
I like that they didn't have a lot.
Huh?
They're
I
gonna
like
get the lab printed off for tomorrow.
I can do that.
Okay. Would I stay or could you just like email it to me?
Oh, just give me 1 second.
Because I did.